this video, we're going to be looking at our Chapter 3 review. This will be a review over our differentiation techniques and our application problems. So let's look at problem number 1. Find an equation of the tangent line to the curve of x squared minus y squared equals 1 at the point 4 square root of 15. Let's take the derivative of the equation implicitly. So we would have, let me change the colors here, we would have 2x minus 2y times y prime equals 0. So we will subtract 2x from both sides, divide by negative 2y, and then we can reduce to x divided by y. So there's our derivative. Now we want to find an equation of the tangent line to the curve, so our goal is to find the equation y equals mx plus b for that tangent line. So let's find the slope first. So we have y prime equals x divided by y. So the slope of the line at the point 4 square root of 15, we're going to plug in our x value and our y value to our derivative. So we would have 4 divided by the square root of 15 for our slope. So that's the slope of our line. So we have y equals 4 divided by the square root of 15 x plus b. Now to find the y-intercept, we're going to plug in that point, which would be on the line as well as the equation x squared minus y squared equals 1. So the y value would be the square root of 15, and the x value would be 4. So if we subtracted, we would get the square root of 15 minus 6 over the square root of 15 equals our b. And we could get a common denominator. So here we would get 15 minus 16 all divided by the square root of 15. That is negative 1 over the square root of 15. And if we rationalize the denominator, we'd have negative square root of 15 all over 15. So the equation of our tangent line at this point would be y equals, we found the slope of the line to be 4 divided by the square root of 15 x, and then we found our y-intercept here to be minus the square root of 15 all over 15. Okay, part 2, or number 2, use logarithmic differentiation to find the derivative of y equals x to the x power. So let's move this up a little bit. So using logarithmic differentiation to find this derivative, we know when we have this form, y equals an f of x raised to a g of x, we use logarithmic differentiation. Now, the steps in logarithmic differentiation, we take the natural log of both sides of the equation. Now, the reason we take the natural log of both sides is so that we can now bring down one of the properties of logarithms. Says we can bring down this x in front. We're not taking derivative yet. We're just using properties of logarithms. Now we can take the derivative. The derivative of natural log of y with respect to x. We're taking the derivative with respect to x. So here we're taking the derivative with respect to x, and that would be the derivative of natural log of y is y prime over y. Now we're going to be taking the derivative of the right side of the equation. So we're going to take the derivative again with respect to x of our x ln of x. Now here we're going to have to apply the product rule. So we would have the first times the derivative of the second plus the second times the derivative of the first. So we would have y prime divided by y equals, so we have x times the derivative of the natural log of x is 1 over x plus the natural log of x, and then the derivative here of x is just 1. So if we clean that up a little bit, we'd have y prime divided by y equals x divided by x, which is 1, plus ln of x. Now we're going to multiply both sides of the equation by y so that we can get y prime by itself. So we'd have y prime equals y times 1 plus the natural log of x. So if we replaced y with x raised to the square root of, or x raised to the power of x, that was our original function. That's what y equals. And then we'd have 1 plus our natural log of x. That didn't come out real well, but that's the natural log of x in parentheses. Number 3, find the derivative of y cubed minus x squared equals x times y. Again, we're going to take the derivative implicitly. Now when we take the derivative of y cubed, we would have 3 3y squared times y prime minus 2x. Now we have to apply the product rule. So we would have the first times the derivative of the second plus the second times the derivative of the first. So we have 3y squared times y prime minus 2x equals x y prime plus y. Now we're going to get all of our y primes on one side of the equation. So everything that has a y prime, I'm going to get on the left side of the equation. So I would subtract x y prime. Then anything that does not have a y prime, I'm going to take to the right side of the equation. So we would have plus 2x. Now we could factor out a y prime. So we'd have y prime, and we'd have 3y squared minus x equals our y plus 2x. And then divide by the quantity 3y squared minus x. And there we have solved for y prime. Number 4, linearize the function y equals ln of x at the point a equals 2 and estimate the value of ln of 2.1. Then compare with the differential dy. So first of all, let's linearize this. Now, the idea for these types of problems is that, let me draw a diagram here. We're going to take our function ln of x, and then we're going to linearize it at 2. So we're going to create the equation of this tangent line, and then we're going to use the tangent line to estimate values of the function itself. So linearization is just creating the equation of the tangent line at a particular point. So if we want to create the equation of that tangent line, and remember, there are two different ways we could do this. You can use the form y equals mx plus b to get the equation of your tangent line, or you can use y minus y sub 1 equals f prime of x, x minus your x sub 1. The first one I wrote was the slope-intercept form, and the second one is the point-slope form. Either one you want to use is fine. So let's look at, we need to find here this m here in this equation is the same as the slope of the tangent line here. So let's find the slope of the tangent line first of all. So we're trying to find y prime. So the derivative of the natural log is 1 over x. So we are trying to find, y prime of 2. So we're trying to find y prime of 2, which would be 1/2. So the equation of our tangent line so far is y equals 1/2 x plus b. So we need a point for x and y to plug in so we can find b. Now we know the x value is 2. Gave it to us here. That's where we're trying to linearize. So looking back at the little graph I drew here, if x is 2, the y value, well, this function is y equals ln of x. So the y value would be ln of 2. And I'm going to use the exact value for right now. So we would have times 2 plus b. So we would have ln of 2 minus 1 equals b. Now if you estimated ln of 2, which is about 0.69, we'd have 0.69 minus 1 equals b, or b equals negative 0.31. All right, so we have the equation of our tangent line now, which would be 1/2 x minus, and I'll just use the decimal approximation, negative 0.31. Then it said estimate the value of ln of 2.1 using our linearization. So what we would do is we would then plug in ln of x is, now we're plugging in the value 2.1 here. We're using this equation of the tangent line to estimate the value of ln of 2.1. So the x value that we would plug in is 2.1. So we would have 1/2 times 2.1 minus our 0.31. So if we did that calculation, we would have 2.1 divided by 2, and that gives us 1.05. So minus our 0.31. And so if we subtract 0.31, we get 0.74. So we use the equation of the tangent line to estimate the value of the natural log of 2.1. Now it says then compare with the differential dy. Well, dy equals f prime of 2 times our delta x. So dy, now the derivative evaluated at 2, the derivative is 1 over x, so we'd have 1/2. And then the change in x. Now see, we are, our value that we're looking at is a equals 2. Now, if we're trying to evaluate 2.1, what is the change in the x value from 2 to 2.1? That's what we're plugging in for dx. So we have 0.1 divided by 2 gives us 0.05. Now you may look at the result that we got here and say that's not close to 0.05. However, remember, let's go back to our little graph. Let's just say this is 2.1 here. dy is actually only this value right here. This would be our dy here. That's dy. So that's what we're saying is 0.05. Now, when we use the linearization to find the value of ln of 2.1, or estimate the value, that was finding this value from here all the way up to here. That gave us 0.74. So that value would be 0.74. So in order to compare our dy with our linearization value, do you see that we would have to add in this actual value? We would have to add in this actual value from here to here. So that is why these values are not equivalent, because the dy is only finding that little value up top there, where the linearization was giving us from the x-axis all the way up to the line. All right, let's take a look at the next problem. And if you, I know this graph up here is a little bit messy now, and it would be hard to work with that. But if you want to take a look at comparing your two values to verify, yeah, those are about the same, you could then go back and look at the value of that blue line that I drew up from the x-axis and add that in to compare it to your linearization, and you'll see those values would be very close to each other. Okay, let's look at the next problem. A plane is flying horizontally at an altitude of 1 mile and a speed of 450 miles per hour, passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So drawing the representation of what's going on here, it flies over a radar station. So let's say this is our radar station, and it's flying 1 mile above the radar station, and let's say it's moving in this direction, and it's moving at a speed of 450 miles per hour. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So the distance between the radar station and the plane would be this distance here. So what we have been given, the given information, is that the speed of the plane, dA dt, I'll say, is 450 miles per hour. And I don't know if it's going to let me clean this up a little bit. So in our diagram, A would be the position of the plane, because dA dt is a velocity. So I'm going to let A represent the distance the plane has traveled past that radar station. So the distance from here to here, I'm letting represent A. Now, what are we trying to find? We are trying to find the rate at which the distance from the plane to the station is increasing. I'm going to let that be represented by x. So that's this distance right here, x. So we're trying to find dx dt. And we need to find this at a particular instant. So when are we trying to find dx dt? It says find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So it doesn't say the horizontal distance, a. It says the distance from the plane to the station. So that would be when x equals 2. So let's see if we can find an equation that relates our variables together now. So we need to relate together ax in an equation. And we can see here this would be a right angle, so we could use the Pythagorean theorem. Now think about what's happening in this situation. As the plane is moving further and further away, a changes. And also x changes. But the leg of the triangle that we have labeled as 1 mile, that will not be changing. So that's a constant in this problem. So we could say our equation is a squared plus 1 squared equals x squared, just using the Pythagorean theorem. So now we can find our related rate equation by taking the derivative with respect to time. So the derivative with respect to time would be 2 times a dA dt. Now the derivative of 1 is 0. So then we'd have the derivative of x squared with respect to time Now let's look back and see what information we can plug in. We do have A, that's 450 miles per hour. So that's our dA dt. Now A, so it doesn't get confusing down here, let me just put A in here and plug in the given information first, and then we'll go back and see if there's anything missing. Okay, then we have 2 times x. Now at the instant we're looking for dx dt, x equals 2. So we can plug in 2 at this point for x, because we want to find dx dt when x equals 2. Now we're missing A. Well, let's look back at the diagram, and we see that we have the triangle at this instant, x equals 2, and the other leg is always 1. So we should be able to solve for A at this instant. So we would have 2 squared equals 1 squared plus A squared. So A squared equals 4 minus 1, or A would equal the square root of 3. Now we don't need the plus or minus, we don't need the negative sign, because this is going to be a distance, so that's always positive. So now we have our value for A. So that would be the square root of 3. And we have all of the information now to solve for dx dt. So if you multiplied everything together, you would have 2 times 450 is 900. Then we'd multiply that by the square root of 3. And that would give us, and I'm just going to round to the hundredths. and then you could divide by 4. So dx dt equals 389.71, and that will be miles per hour. A construction worker pulls a 16-foot plank up the side of a building under construction by means of a rope tied to the end of the plank. Assume the opposite end of the plank follows a path perpendicular to the wall of the building, and the worker pulls the rope at the rate of 0.5 feet per second. How fast is the end of the plank sliding along the ground when it is 8 feet from the wall of the building? So first of all, let's draw a diagram. So we have a plank being pulled up the side of the building. So here we have this rope, and somebody's pulling this up the side of the building. So this is moving up this way, and the bottom of the board is moving this way. So the given information and there's one other thing I could list here. It's a 16-foot plank, so we can list that in our diagram. So it says that assume the opposite end of the plank follows a perpendicular path to the wall of the building, and the worker pulls the rope at the rate of 0.5 feet per second. So if I say this side over here, the distance from the ground and the building to where the top of the plank is, I'm going to say that is y, that distance. So that's a position function. So if I take the derivative of a position function, it gives me the velocity. So we'd have 0.5 feet per second. What are we trying to find? It says how fast is the end, and here's what we're trying to find. How fast is the end of the plank sliding along the ground when it is 8 feet from the wall? So I'm going to label the distance that the plank is, the bottom of the plank, to where the building and the ground intersect. I'm going to label that as x. So we would be wanting to find dx dt. And when do we want to find dx dt? When the bottom of the plank is 8 feet from the wall. So when x equals 8. So let's see if we can find an equation that relates these variables together. And we can see this would form a 90-degree angle between the building and the ground. So we could use the Pythagorean theorem. And again, you can see that as this is going on, y is changing, x is changing, but the length of the ladder is not changing. That's always going to be 16 feet. So that's something that we can plug in as a constant to this equation. Now we're going to find our related rate equation, which would be 2y dy dt plus 2x dx dt, and the derivative of 16 squared is 0. So what information can we plug in at this point? Dy dt, that's what we're trying to, that's some given information. We're trying to find dx dt. Dy dt is given as feet per second. Now, plus 2 times x. Now, at the instant we're trying to find dx dt, x equals 8. So now we can plug that in. And dx dt, that's what we're trying to find. That all equals 0. So we have to find y. Well, looking back at our triangle, we know that at this instant, we said x equals 8. We know the hypotenuse is always 16, so we're trying to find y at this instant. So we could use the Pythagorean theorem. Y squared plus 8 squared equals 16 squared. So 16 squared is 256. So we would have y, I don't know if I can squeeze it in here, squared equals 256 minus 64. So when we take 256 minus 64 and then take the square root, you get 13.86. And again, I'm rounding to the hundredths. So now we have our value for y, 13.86. Now, in this calculation, you could leave this value here in exact form, and that's the best thing to do. We could leave that as the square root of 256 minus 64, so then we wouldn't get any rounding errors. So if we take our 13.86 times 2, but then we're going to divide that by 2, so we're going to get back to our 13.86. We'll subtract that to the other side and then divide it by 16 to get 0.866. So if we solve for this, we get dx dt, and now this would give us a negative value, so we get negative 0.866. Oops, I was rounding to the hundredth, so let's go with 87, and that would be feet per second. Now some practice finding derivatives. Okay, the first one, y prime. Now we just have to remember the derivative of 3 to the x. If we want to find the derivative of 3, see if I can fit it in over here, 3 to the x power, we know the derivative of exponential function. This would give us ln of 3 times 3 to the x. Now we're multiplying that times 5. So our y prime would be 5 ln of 3 times 3 to the x. That's the derivative of this piece. And now we're going to be looking at the derivative of cosine of 2x. Now the derivative of cosine of 2x, the inside function is 2x. if you wanted to say that's your u, and your outside function would be cosine of u. So we take the derivative of these two, multiply them together. Y prime then would be negative sine of u, but u is 2x, and then u prime is just 2. So we would multiply those together to get negative 2 sine of 2x. So there's our derivative. Okay, next problem. We have e to the negative 2x times this quantity. So we can apply the product rule, but I'm going to rewrite this first. This would be the same as e to the negative 2x times negative, and see this here is negative 1 all over the 4th root of t cubed, which is t to the 3/4 power. But I'm going to bring that up into the numerator as negative 3/4. So now let's apply the product rule. We would have the first, so this is going to be our y prime, first times the derivative of the second plus the second times the derivative of the first. So the derivative of negative t to the negative 3/4, so let me bring that down over here. We would have e to the negative 2x, the derivative. Now I'm going to bring the negative 3/4 down in front, so it becomes a positive 3/4 t, and now we're going to just subtract 1, but I'm going to just get a common denominator of 4/4. So it would be to the negative 7/4 plus negative t to the negative 3/4. Now remember the rule for the derivative of an e to the f of x. It is e to the f of x times f prime of x. So this would be e to the negative 2 to the power of negative 2x times the derivative of negative 2x, which would be negative 2. And now you just have some simplifying to do. I'm just going to do a little bit of simplifying here, but then leave the rest to you. So here in the first term, we could take e to the negative 2x down into the denominator with the t to the negative 7/4. So we'd only have a 3 in the numerator. We'd have e to the 2x. And then we have this 3/4. And I'm going to pull that 3/4 all the way out front so it doesn't get so confusing when we look at simplifying that. So if we pulled the 3/4 all the way out to the front, then we would just have t to the 7/4 and you can see how that would simplify. We'd have 9 over 4 e to the 2x times t to the 7/4. And this negative here, I'm just going to go ahead and pull that out front here, but then I see there's another negative right here, so that's actually going to end up being a positive. Now when we take both of these quantities down to the denominator, we'd only have a 2 in the numerator, and then we'd have a t to the 3/4 times e raised to the 2x. Number 8 is implicit differentiation. So we would have to apply the product rule first. We'd have to say the first times the derivative of the second plus the second times the derivative of the first. Plus, now the derivative of 2y squared would be 4y times y prime derivative of x is 1, and then we would have minus 5y prime. So now if we take the derivatives over here, we would have times 3y squared y prime plus y cubed times 2x plus 4y y prime, and then you would get all of your y primes on the same side, factor that out, and then divide the quantity over to the right side that doesn't have y primes in it. So I'm going to leave a lot of that to you again, but if we got all of the terms with y prime in them, we'd have 3x squared y prime. That's our first term. Then we have plus a 4y y prime. Then we would subtract 1 from the other side. I'm sorry, we don't want the 1. We want the plus 5y prime. So we'd have plus 5y prime equals, that's a plus. So we would have this term here, we're taken to the other side, so we would have 1 minus 2xy cubed. And then we could factor out our y prime, and then we could divide over the factor that doesn't contain the y prime. The next problem. I like to think of this problem as the peanut M&M. If we have a shell on the outside, chocolate, and then on the very inside a peanut, if we take and let that dissolve in our mouth, the outside shell would first dissolve. So we'd be looking at the rate of the change of the outside function, but the insides, the chocolate and the peanut, would not change. So the derivative of the outside function would be cosine, and then we'd leave the inside the same, because we haven't gotten to the chocolate or the peanut yet. Now, once the outside shell is gone, we get to the chocolate. So we move to the next inner function. Now we're going to look at the rate of change of the chocolate. Well, the derivative of cosine is negative sine, but the peanut stays the same. And then finally we look at the rate of change of the very inside function, which would be the derivative of sine of x would be cosine of x. Now if you wanted to do this with your u, your inside function, and y, the outside function, you can see we have 3 functions here. So we'd actually start with v equals the innermost function. Then we'd go u equals cosine of v, and do you see this would give us cosine of the sine of x? And then the outside function would be the sine of u. And then you take the derivative of each one of these. So the cosine of u times negative sine of v times the derivative of sine x is cosine of x. Now if you made the back substitutions, u we said equals cosine of v, but v equals sine of x, so we'd have cosine of v sine of x. So you can see this is matching up to what we have above. Then we'd have negative sine v is the sine of x, and then lastly we have times our cosine of x. So either technique you want to use works just fine. You get the exact same answer. Okay, we have another composition of functions here. So again, if you wanted to, here I see 1, 2, 3, 4 functions. So if we want to let w equal 1 plus x cubed, v equals the square root of w, u would equal the tangent of v, and then y would equal the sine of u. Take the derivative of each one of those, multiply them back together, and back substitute. So first we'd have the derivative of sine of u, cosine of u. There's our y prime. U prime would be secant squared of v. V prime would be 1 all over 2 square roots of w, and then w, the derivative is 3x squared. Now when we multiply these all back together, cosine of u is the tangent of v, but v is the square root of w, and w is 1 plus x cubed. So there's our y prime. Secant squared, now our u prime would be secant squared of v, but v is the square root of w, and w is 1 plus x cubed. And then we have times v prime, which is 1 all over 2 square roots of w, but we're going to replace w with 1 plus x cubed, and then times our w prime. And that is our derivative. And if you work, I typically like to work from the inside when I use the other technique. I look at the innermost function, which is 1 plus x cubed, and so I would say, well, the derivative of that is 3x squared. Then I start moving outward. I see a square root function, so I know the derivative of the square root function is 1 over 2 square roots of x. And then I start moving out. Secant squared is the derivative of tangent, leaving the other two functions alone. And then the outside function is your cosine, leaving your other three functions alone. All right, next problem. We have, let's get a little bit of room here. The next problem we have, it looks like we're going to need to use the quotient rule. So we would apply the quotient rule, bottom times the derivative of the top function minus the top function times the derivative of the bottom function, all over the bottom function squared. Now, simplifying this, we'd have x. Now, the derivative of the sine of kx, again, think of your inside function and outside function. Your inside function is kx, so the derivative of that is just k. And then the derivative of the outside function is cosine, but you leave the inner function alone. Minus the sine of kx times the derivative of x, which is just 1, and that's all over x squared. So there is our derivative. Next problem, find dy dx if y equals ln of the square root of x divided by 5 minus x. Let's use properties of logarithms. So we could write this as ln of x to the 1/2 minus ln of 5 minus x. Now that 1/2 we could bring down in front. Now when we take the derivative, y prime, the derivative of the natural log is just 1 over x. So we'd have 1/2 times 1 over x. And we know the derivative, let me write that over here, the derivative of the natural log of an f of x, we've gone through this process and we know that this is f prime of x all divided by f of x. That's the general rule. So let's apply that here. So the inside function, the derivative, would just be -1. That's the derivative of 5 minus x all over the inside function, 5 minus x. So if we just clean that up a little bit, we would have the derivative is 1 over 2x plus our 1 all over 5 minus x. A coin is dropped from the height of 750 feet. The height, s, measured in feet at time t, measured in seconds, is given by this function, -16t squared plus 750. Find the average velocity on the interval 1 to 3. We know the average velocity. We would take s of 3 minus s of 1 all divided by 3 minus 1. Remember, that's the slope of the secant line. So we plug the values, 1 and 3, into the function, subtract them. This is our difference quotient. So when we plug those values in, we'd have -16 3 squared minus plus 750 minus, then we would have -16 times 1 squared plus 750 all divided by 2. So 3 squared is 9, and so 9 times 16 is 144, so we'd have -144. Now, do you notice that this 750, when we distribute the negative sign here, is going to cancel with that -750. So here, when I multiply this negative, it becomes +16, so plus 16 divided by 2. So we have -128 divided by 2 give us -64 feet per second. That would be our average velocity. Find the instantaneous velocity when t equals 3. Well, the instantaneous velocity we know we can find if we have the velocity function, which comes from the derivative of the position function. So the derivative of the position function is negative 32t, and then the 750 goes to 0. So we are looking for v of 3. So we get negative 32 times 3, which is negative 96, and it would be feet per second in this problem. How long does it take for the coin to hit the ground? So let's just remind ourselves the position function is negative 16t squared plus 750 So our position function was s of t equals negative 16t squared plus 750. So it's asking how long does it take for the coin to hit the ground. Well, if this is our position function, we want to know when is the height 0. So when we solved for t here, if we subtracted 750 and then divided by 16, and then we're going to take the square root. So t would equal 6.85, and that would be seconds. Find the velocity of the coin when it hits the ground. Well, again, to find the velocity, we know the velocity function comes from the derivative of the position function. So that would be negative 32t. So we're trying to find v of 6.85. That would be the velocity when the coin, that's the instant the coin hits the ground. So if we found v of 6.85, we would get negative 219.2. And that would be feet per second. So that's just plugging in 6.85 to our velocity function. So we'd have 6.85 times 32, which is times negative 32, which is negative 219.2. A woman walks along a straight path at a speed of 5 feet per second. A searchlight located on the ground 15 feet from the path is kept focused on the woman. At what rate is the searchlight rotating when the woman is 17 feet from the point on the path closest to the searchlight? So here we have a searchlight, and we have this is 15 feet from the path that she's walking on in this direction, and she is walking at a speed of 5 feet per second. And so the woman is here, and the searchlight is keeping focused on the woman. So we're trying to find the rate at which the searchlight is rotating. So that would be this angle right here. That would be our theta. So our given information is the speed of the woman, dw dt, which is 5 feet per second. And so w represents the position of the woman. So I'm going to label this side of the triangle as w. So w represents the distance this woman is on the path that was closest to the searchlight, so it would be perpendicular, so this would be 90 degrees here, from that point to where she is W. What are we trying to find? We're trying to find the rate at which the searchlight is rotating. So that indicates we're looking for the rate of change of the rotation of this searchlight. So I'm going to label that as d theta dt, where theta represents the position of the spotlight. And we are trying to find this when, let's go back, it says when the woman is 17 feet from the point on the path closest to the searchlight. So that would be when W equals 17. So an equation that relates our variables together, it looks like we're going to have to use a trig function. And we have the angle, theta, we have the opposite side and the adjacent side. So it appears that we're going to use the tangent of theta equals opposite over adjacent. So our related rate equation, we take the derivative with respect to time. We would get secant squared theta times d theta dt, chain rule. Now this right here, the derivative of this, we don't have to use the quotient rule. This is just 1 over 15 times w. So the derivative would just be w prime, or dw dt, times 1/15. So 1/15 times dw dt. So what information can we plug in? We have dw dt. So let's plug in our given information. So we have 1/15 times the woman's speed, which is 5 feet per second. Now how are we going to find the secant of theta? Well, we go back to our triangle, and we know that the secant of an angle equals the hypotenuse over the adjacent side. Well, we don't have the hypotenuse, but we can find it, because at this instant, when w equals 17, we would be able to find the hypotenuse. So using the Pythagorean theorem, we'd have 15 squared plus 17 squared, and I'm going to just go ahead and take the square root, and that would be w. So now we have, I'm sorry, that's not w, that's our hypotenuse. When w equals 17. So we have now all of the information to find the secant of theta. The secant of theta is h over a, hypotenuse over adjacent. We just found the hypotenuse is 15 squared plus 17 squared, all divided by the adjacent side, which is 15. So now we can plug that in for, and remember, secant squared theta is the same thing as secant theta quantity squared. So we're going to plug in our square root of 15 squared plus 17 squared, all divided by 15, and that quantity then would be squared. And on the right side of the equation, we have 5 divided by 15, which would reduce to 1 over 3. So now you have all the information to solve for d theta dt. So I'm going to have to do this calculation. So 15 squared is 225 plus our 17 squared is 289. And if we take the square root of that and then divide it by 15, oops, my calculator. So we have this divided by 15, 1.51. So we would have 1.51, and then over here we had 0.33. So our d theta dt equals 1/3, and then we're going to divide both sides by our 1.51. So when we do that, we should get our d theta dt, which is 0.22. So 0.22, and that would be radians or rads per second. Suppose x and y are differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x equals 1. Given that dx dt equals 2 when x equals 1. So we're trying to find dy dt and we're trying to find that when x equals 1. So we're going to go back to this equation and take the derivative. That would be our equation. So our related rate equation would be taking the derivative. So dy dt equals 2x dx dt, and then 3 goes to 0. So we're trying to find dy dt. And it says find dy dt when x equals 1, so we'll just plug 1 in. And given that dx dt equals 2, it told us that dx dt equals 2 when x equals 1. So we can plug in 2 here, and we have our dy dt equals 4. Find a formula for f to the nth derivative of x. Now, with these types of problems, we are looking for a pattern. So if we take f of x and rewrite it as 1 minus x to the negative 2 power, f prime of x would equal negative 2 times 1 minus x. Now we're subtracting 1 from the exponent, times the derivative of the inside function. So f double prime of x. So here in this one, this would be a positive 2. So it would just be 2 times 1 minus x to the negative 3. So taking the second derivative, we would have negative 6 times 1 minus x, subtract 1 from the exponent, times the derivative of the inside function. So we get 6 times 1 minus x to the negative 4. Now let's take one more derivative and see if we can see a pattern here. If we take the derivative now of this, and see this 2 right here, I multiplied that by this 3 when we found the derivative. So this is actually 2 times negative 3, and then we have our 4 coming down, negative 4, and we'd have 1 minus x to the negative 5 times negative 1. All right, so I can see in here that I have a mistake with my signs, so I'm just going to redo this quickly here. So let's look at that again. Let's just do it from this right here. We would have negative 4, bring down the negative 4, times our 6, 1 minus x, now we subtract 1 from the exponent, and then multiply by the derivative of the inside. And so here we get our 24 times 1 minus x to the negative 5th power. Now I think we can look at our pattern here and develop a derivative for f to the n. So this one I said was 2 times 3 times our 1 minus x to the negative 4. This one here would be our 2 times 3 times 4 times 1 minus x to the negative 5. And so we're going to look at the derivative. This is the second derivative, and this right here is 3 factorial. Here's the third derivative. Right here, this is 4 factorial. So we can see that factorial is 1 less than the derivative. So we could represent that as n minus 1 factorial. So look at your third derivative. I needed a plus in there. I think I said minus. N plus 1 factorial. If we take the second derivative, we can see it's 3 factorial. If we take the third derivative, we can see it's 4 factorial. If I take the nth derivative, I can see it's the n plus 1th factorial. And then we have our 1 minus x. And then we're going to relate the powers now. These powers back to which derivative we have taken. Well, the first derivative, this is negative 3. Second derivative, negative 4. Third derivative, it's negative 5. So it looks like n plus 2, but they're negative. So if we put negative n plus 2, you can see, go back to your first derivative now, this one. If I say this is the first derivative, I would have n plus 2, 1 plus 2, which gives me 3 right here. For this one, second derivative, I'd have 2 plus 2, which would give me 4. The third derivative, I would have 3 plus 2, which gives me 5. But then they're all negative. And you could rewrite that as n plus 1 factorial divided by 1 minus x to the n plus 1, because you could take that negative exponent to the denominator. So we could say this 1 minus x all to the n plus 1. And that would be our formula for the nth derivative of this function here. Find y double prime. if y of r equals, okay, so our first derivative would be 1 all over 2 square roots of r. Now this one, see, this is r to the 1/2 plus r to the 1/3. So I'm just applying the power rule. I bring the 1/2 down in front, then subtract 1, which would give me negative 1/2. And I'm going to do the same with the second one. We would have 1/3 r, then we'll subtract 1, which would give us negative 2/3. So there's the first derivative. So finding the second derivative, if we wanted to leave this in the form of, see, this one right here would be 1/2 r to the negative 1/2, and then we got plus 1/3 r to the negative 2/3. Now we're trying to find the second derivative. So if we apply the power rule again, we'd get negative 1/4 and then we'll subtract 1 from the power to get negative 3/2 plus, now we're bringing the exponent and multiplying it times our 1/3, bringing that down in front. So we'd have a negative 2/9 r, now we're going to subtract 1 from the exponent, negative 5/3. So our y double prime if we rewrote it back in, I'm going to put it in rational exponents first, and then we'll rewrite it. So we'd have r to the 5/3. And if we rewrote this back in square root form, we would have the square root of r cubed minus 2 over 9 cube root of r to the 5th. And there's our second derivative.